So it's happens in dark, of course, but is it that we see the boundary of it at 40 degrees latitude? Because that's
So it actually, it depends on how strong the solar storm is. Last night I saw aurora over my head and even a bit south of overhead. It was that strong. So yeah, and so yes, if I send an email out tonight saying you should go out and see the aurora, go out and see the aurora! I'm just saying. That doesn't matter! It doesn't matter! Stay up till 4 if you have to see the aurora! Can you tell how I feel?
I went outside, it wasn't there, so I was like, I missed it. No, I guess it like pulses too, right?
See, no, it's not pulsing so much. When I sent the email, I was like, it's green, it's there. About 10, 15 minutes later, I'm like, uh-oh. And I mean, it exploded. It was just everywhere. So, you know, just the whole northern sky. It was fantastic. You must not miss this. So I'm going to make everybody look at the photo that Estelle took of the student observatory, right there, right? I saw it, right? Student observatory last night. See that? See that? See that? See that? Hey, look at that. Wow. Yeah, see that? See that? See that? Wow. See that? Do you see that? Do you see that? You should try to see that.
I didn't see it.
Oh, you didn't see it yet? Oh. Do you see that?
Yes.
Yes.
Wow.
That's right. That's right. Do you see that? Look at that. It's magnificent. I have no idea what it'll look like on the camera, but in any case, so yeah. Okay. Back to other stuff, shall we? So let's talk about spectral lines, because they are an important diagnostic in astrophysics. And so we should, any astrophysics major ought to know something about the structure of spectral lines. Maybe someday you would even use it professionally to learn things. So, you know, because up to now, right, you've probably got this understanding in terms of, well, you know, electrons jumping levels, and so they absorb specific wavelengths and all that sort of thing. But we can go a lot further. We can talk about in much more detail what a line profile actually looks like. In other words, a detailed plot of intensity versus wavelength, so that you can see the details of the dip in brightness associated with the absorption line, if we're talking about an absorption line here, which we usually are when we're talking about stars. So, structure of spectral lines. Now, if you see the aurora, you're seeing spectral lines too. Those are emission lines. Those are emission lines created by oxygen atoms, nitrogen molecules up in the atmosphere when high energy particles are striking them, kicking electrons up to higher levels, and then when they drop back down, they can emit visible spectral lines. So if you took a spectrometer, you'd see an emission line spectrum of the aurora. Spectroscopy, well, at least spectral lines in action in a beautiful way. Anyway, structure of spectral lines. We're going to go over a bunch of contributions to this. And then it's almost like on the final exam, I'll say explain each of these contributions to, you know, spectral line formation here. So first we need to establish some vocabulary here. So here is a plot versus lambda of flux at wavelength lambda over the flux of the continuum. So it's F sub c there, that stands for continuum. So that's the local continuum brightness. In other words, we're looking at a little narrow region of the spectrum near the spectral line. The continuum is how bright it is outside the spectral line. And remember that this is always per unit wavelength, right? In other words, the actual watts per square meter is F lambda d lambda. You have to talk about a little d lambda to talk about the actual flux that'll come through some hypothetical really narrow band filter that only lets in some narrow range d lambda of wavelengths. And so if we are Well, okay, so first I'll kind of just sketch a line, so to speak, sketch a profile. Looks something like this. It's a dip, right? So it's not just a spike downwards. It's got some width to it. I've exaggerated it here for clarity. Many spectral lines wouldn't be this wide compared to their depth, if you will. And so the continuum is f lambda over fc is 1, because in other words, outside the spectral line, outside the range of wavelengths that the spectral line's associated with absorption by atoms, then it's as bright as the continuum. It is the continuum, so f lambda over fc is 1 out there. And let's just draw a dashed line to show, well, if those atoms weren't even present that are making this spectral line, then you just get a horizontal line there for the f lambda over fc at all those points. And want to introduce a concept called the equivalent width of the line, because we want to say, how broad is the spectral line? But, well, you know, really, if you think about it, there's no one way to describe how wide this thing is. There's various measures you could decide, but it's not like it all of a sudden goes from continuum down to black and then back up to continuum again. If it did, you could say, oh, well, all the wavelengths that are being absorbed, that range is the width of the spectral line in wavelength. But no, you could come up with multiple definitions of the quote-unquote width of the spectral line. Here's a commonly used one, what we call the equivalent width. And it works like this, and who knows if my drawing will accurately capture this, but the idea is there. So, and if I do this right, this should be nice and symmetrical. So I'm going to say, from there to there, this is what we call the equivalent width The equivalent width of a line is the width of a completely black line that would have the same area as the spectral line. Area meaning, like on my curve here, of below the continuum. Like, in other words, think of the area below the continuum. If you integrated below the continuum, what's the area there? The equivalent width is how wide a completely black line would be. In other words, one where literally there's no light being passed through over some range of wavelengths. And essentially you're saying, well, how wide a range of wavelengths of complete blackness would sort of absorb the same amount of light as the actual spectral line is associated with. So the equivalent of W of a line is the width of a completely black line, the width, and by that we mean in wavelength, of a completely black line no light's getting through, that has the same area as the actual spectral line. And then I'll start being more specific about what we mean by that. And so this is a very common measure. If you read papers that involve any kind of spectroscopy, you'll see equivalent widths mentioned all the time for spectral lines as the actual spectral. That's all. As the actual spectral line. So, to say what we mean by that, so let me kind of hash in that rectangle right there. So that's the area of that rectangle. So it would be an area essentially in wavelength, if you will, because the y-axis is dimensionless. It's a ratio of fluxes there. And we could also talk about hash it the other direction. The area under the continuum of the actual spectral line If those two areas are equal, well, that's the equivalent width of the spectral line, how wide the box needs to be in order to have the same areas there. And, oh, I should do the cheat thing. I think Dr. Trees does this all the time, uses chalk of different colors. Yeah, I'm going to do that now. If you're using your iPad or something, why, you can probably duplicate this, right? If you're just using a pencil or a pen, well, too bad. You just, I don't know, just do it best you can to indicate what I'm getting at here. So, what I just drew there in green is what we call the depth of the line at a given wavelength. So that's the depth of the line at the wavelength indicated, you know, wherever it is along the lambda axis. So it's a function of lambda. In other words, it's just how far you are below the continuum is what it comes down to. So if this was 40% of the continuum brightness right here, well, then the depth at that location is 60%, 0.6 at that location. Make sense? Can you see that, Kathleen? So this, oh boy, this says depth of line at the lambda indicated. Yeah, and I drew a green arrow that goes from the continuum down to the profile of the line, the curve of the line right there. Get some glasses.
Well, it's like the colors.
Oh, I know, that's true, yes. No. I was just inspired by the aurora last night, you know, I felt it, yeah, see, so, right, yes. Yeah, so depth of the line at the lambda indicated is what that so very clearly says illegibly because it's so dark. Okay, here is lambda naught, where the line is deepest, where it's darkest. That's lambda naught, kind of the central wavelength, if you will. And while there's no hard and fast definition of exactly how wide a region this is, we call the bottom of the dip, if you will. That's the core. That's the core of the line. And again, you'll see this in papers. The line cores are blah, 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 blah. And on the other side, like when you're getting closer to the continuum, closer up to the continuum, those are the wings of the spectral line. Those are the line wings. That's just the terminology. Yes?
I did not understand what's the core.
The core is just this part of the spectral line. In other words, the central part of the spectral line. Well, from over what range? It's just the central part of the spectral line. Yeah, it's just left kind of vague like that. And the wings are the edges of the spectral line. Yep. So let's give a specific definition of the depth. The depth is equal to the continuum flux minus F lambda divided by the continuum flux. In other words, it's kind of like, you know, how much light you've lost divided by the continuum flux. It's how much dimmer you are than the continuum divided by the continuum flux. So in the continuum, at a wavelength which is in the continuum, what's the depth? Yeah, it's 0 at that point because at the outside the wings where we're back in the continuum, then F lambda is equal to, F sub lambda is equal to F sub C, right? F is a function, F lambda, the flux is a function of wavelength, flux per unit wavelength is a function of wavelength, blah, 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 is equal to the continuum flux. So the depth is 0 there. Does that make sense? Make sense? Not make sense? Okay. What would make the depth equal to 1? Where would the depth be 1? It's not 1 anywhere for this profile right here, but what would make it 1? What would f sub lambda have to be to make the depth equal to 1? 0, right? If there's no light coming through, then the depth is 1. So the depth ranges between 0 and 1, and it's essentially the fraction of the light that's being removed by the presence of the spectral line. So it's 0 if f lambda equals fc, and it's 1 if f lambda equals 0. Seems like a reasonable definition. It's how far below the continuum you are, essentially, as a fraction. It's fractionally how far below the continuum brightness you are. And with your amazing powers of algebra, you may be able to deduce that this is 1 minus f lambda over f continuum, is another way to put it. Just dividing through by fc. So if we want a mathematical definition of the equivalent width, that w over there, a mathematical formula for w, it's w is the integral of depth d lambda. Right, so you just integrate depth d lambda. And so in other words, you're integrating fc minus f lambda over fc d lambda. And the reason we say that is, so this is, right, if you interpret this, this is the area under the continuum associated with the line profile. Well, that wasn't very nice. Yes, it did. It just fell down there. Yes. We actually, I know, we'll never see you again. We'll miss you. Or have fun in hell for breaking off like that. But maybe it wasn't its choice, so maybe I shouldn't be so mean. We actually have a little, what do you call those things, like little pickers that we in principle, but I use those for like, sometimes the erasers go down there. Yeah, and then it's like, well, my arm won't reach into that. So yeah, what do you call those things? Like a trash picker. Do you know what I'm talking about? Yeah, right. Yeah, what's that? Yeah, kind of like that, yeah. I don't know, but they're a GG thing. Yeah, anyway, area under the continuum. That's like the area under the continuum. And if you think about it, well, the continuum, the way we've defined things, has a value of fc over f lambda equals 1. Right, that's the continuum. So in other words, our area under the curve here is under the line y equals 1. And so if I had a box of width w, what's the area of the box? W. W is the area of the box. In other words, in these units, the area of a completely black line of spread in wavelengths W would be W because its height is 1. And so this integral, gives a value W, which would be the area of a completely black line that had a width equal to the value of that integral. But no line is ever completely black anywhere because there's always some light getting emitted by the star at any wavelength. There's some photons escaping. So a completely black light would be a sort of idealization that you never see. And to give a number here, when you do that integral and find out what it is, typically the equivalent width is about 1/100th of a nanometer, about 0.1 nanometer for visible spectral lines, visible wavelength spectral lines. So it's quite narrow. It's only 1/100th of a nanometer or thereabouts, but it ain't zero. Right? Again, it's not that an atom can literally only absorb a particular set of wavelengths, and it has to be exactly those wavelengths. It never happened in that case. You're never going to have a photon with exactly that wavelength. So, in fact, atoms aren't quite that picky, but it is a very narrow range of wavelengths that they like to absorb. So now we have to say, well, why is there a range of wavelengths? After we mention one other measure of the width of the line. Can I erase this? So there's another very common measure of line widths and of many other kinds of widths. Like, you know, in physics, often in the lab, we'll be plotting some quantity, and it'll be like, you see something that kind of looks like that. And you're like, well, how broad is that peak? Whatever the heck it represents. And a very common measure is you say, okay, well, there's probably some baseline, either noise or signal that's just there, even if nothing's happening. And you say, okay, what is the width of the region where you go between 2 points that are at half the maximum above the baseline there? So you go baseline, maximum value, halfway between, and from there to there is what's called the full width at half maximum. Or the full width half max, FWHM. Now for our spectral line, I mean, I just drew like, what if you had an emission line? What if you had some curve? For our spectral line, we're going to go the other way around. We're going to go halfway down to the bottom here, and the full width at half maximum would be orange chalk this time. The full width at half maximum would be like from here to here. FWHM. Go from the continuum to halfway down to the bottom. Like, for example, if this value right here was 0. Is it going to, about 0.2, how far down do I go to find the full width at half maximum? What would be the depth at the 2 points where I'm finding the full width half maximum between? So continuum's 1, the bottom here is 0.2, so what's halfway between those? 6.6, right? 0.6, right? So if that's 0.2, then the spread between where the depth is 0.6 within the line would be its full width at half maximum by this measure. So another measure of the width . And you could do it for an emission line where it'd just be more like what I just drew there. Another measure for the width of a spectral line, or many kinds of peaks in astro parentheses physics, because this does not just apply here. I mean, it just shows up all over the place. is the full width at half maximum. The FWHM for the, right, because you get tired of saying, right, full width at half maximum all the time, so you say FW, actually, well, in writing you say FWHM, in speech you basically usually just say full width at half max. Full width at half maximum which is the distance in nanometers, if we're using that as our measure of wavelength, between the points where the line depth, actually, I lied in my notes, don't listen to that. But I said where the width is, where the depth is a half, that's a lie. I don't know why I put that there. Silly me. Earlier, Dr. Harmon, you're a silly person. Good thing I'm not earlier, Dr. Harmon. Between the points where the depth is halfway between 1 and the minimum. Or I should say halfway between 1 and maximum depth. Okay, does that one make sense? What questions do you have? Which is the distance in nanometers, because we're talking about wavelength here, right? Distance in nanometers, and don't think I mean literally nanometers in space. I mean nanometers in wavelength here, nanometers in wavelength. The distance in nanometers of wavelength between the points where the depth is halfway between 1 and the maximum depth. So for example, with my example here, if the maximum depth at lambda equals lambda naught was 0.2, then the full width at half max is how many angstroms are between the points where the depth is 0.6, because that's halfway between 1 and 0.2. Happiness and joy, or what the hell are you talking about, Dr. Harmon? Yes?
Why is full width at half maximum a special point?
Is especially what?
Why is it a special point?
Oh, no, so it's not a point. It's not a point. The full width at half maximum is a measure of how broad the line is. And so we just say, okay, you know, with something like this, how broad is this, right? Well, in fact, you know, I make it look like it's like, it's suddenly equal to 1 outside the line, but it actually just kind of fades away. It's like, you know, so you actually have to get pretty far away before you're back to the continuum again. So is the line width, should we say the line is all the way from there to there, that many nanometers along the x-axis across? Is it from here to here? Is it from here to here? We have to have some kind of definition of what we mean by how wide is the line, because there's no intrinsic number you can attach to that. You can come up with lots of definitions. For example, the equivalent width is one possible definition. Another one is just say, okay, just go to the halfway points. Go to where it's got down to the depth is half of its maximum value, and just say the distance, the number of nanometers of wavelength between those 2 points is the full width half max. So it's a measure of how wide the line is what we're talking about. It's not a wavelength or anything like that. It's a span in wavelength that is a measure of how wide the line is as a span in wavelength. Okay, does that make sense? Somewhat, yes. Okay, maybe we talk later if you want to make it more than somewhat. What other questions do you have? Okay, so, you know, for example, if lambda naught for some spectral line was, oh, I don't know, 528.332 nanometers, right? If that's 528.32 nanometers, this whole range of wavelengths I've drawn is quite small here. Equivalent widths are typically like 1/100th of a nanometer. And so if this is 528.32 nanometers, this is 528.325 nanometers. And this is 528.315 nanometers. This is a very narrow range of wavelengths that I'm plotting here because we're just looking at one spectral line as part of the star's whole spectrum. Okay? What are your further questions? Let's talk about sources of line broadening then. How come they're not infinitely narrow? Because when we talk about the simple Bohr model picture where we say, oh, electrons can only have very specific energies, or even just the simple quantum picture, the simple like physics even 380 picture of all this. Oh, electrons in an atom can only have very specific energies as dictated by the Schrödinger equation. And for it to absorb a photon, the photon has to have a wavelength that corresponds to the difference in energies between the two levels. If you take all that very literally, you would conclude it has to have an exact specific energy. No plus or minus to it. It has to have some exact specific energy. And therefore, the width of the line would be 0 because it would be only one specific wavelength that could be absorbed. But that's not the case. There's actually a narrow range of wavelengths that can be absorbed. Sources of line broadening. Reasons they're not infinitely narrow like that. So this is, now we're talking quantum physics, we're talking Doppler shifting, lots of stuff involved here. Let's start with the quantum physics involved. Oh man, this Hagoromo chalk is not living up to its reputation today. I'm very sad now. Okay. I have very, okay. Y'all just chill for a few minutes while I go get another piece of chalk. I should probably, no, I should probably leave this on. It's like, yeah. No. All right, so they proudly put their name on the chalk, so they'd better live up to the fact that they're proudly putting their name on the chalk this time. I'm hoping that last piece of chalk was just like, a slip up on the production line or something like that. Okay, so sources of line broadening. Number 1, quantum mechanical effect, natural broadening. Maybe I just need to press a little more lightly. I'm so excited, I'm pushing too hard on the chalk. It's all my fault. Now I feel guilty. I'm sorry, Hagoromo chalk. I should not have abused you like that. Natural broadening due to the finite lifetimes of excited states involved in atomic transitions. So this is a quantum effect. Due to the finite lifetimes of the excited states involved in atomic transitions. So y'all know about the uncertainty principle, right? And it's often stated like delta x, delta p is on the order of h bar. Sometimes we'll say h bar over 2. It's actually, strictly speaking, it's sigma sub x, sigma sub p is greater than or equal to h bar over 2, where the sigmas have a very specific definition. It's comes from finding the expected standard deviation of a bunch of measurements based on probabilities from the wave function. Now, are you aware, and this often is kind of loosely stated as a particle can't have a well-defined momentum and a well-defined position at the same time, and the better you know the momentum, the more poorly you know the position, and vice versa. Are you aware there's also an energy-time uncertainty principle? There is. So there's also an uncertainty principle that says that delta E delta T is on the order of h bar. Delta E is the uncertainty in an orbital's energy. You've been lied to when we say that, oh, there's very specific energies that the orbitals have, that the electron has. If the electron's up in n equals 2, its energy actually isn't perfectly well defined. Delta E is the uncertainty in an orbital's energy due to its finite lifetime, delta T. That's a little bit sloppy language because every electron will decay after a different amount of time, so we're really talking more about like the average lifetime of the particle in the given orbital due to its finite lifetime, delta T. Because if you put an electron into n equals 2 in a hydrogen atom, will it just stay there forever? No. It, quote unquote, to anthropomorphize, wants to lower its energy by dropping into the ground state and give off a photon, right? Well, it turns out that, and I don't know if you ever, I don't know if y'all did this, how many of you have taken quantum 380? How many, right? Did you talk about how x and p are really a Fourier transform pair of variables, and you can understand it in terms of Fourier transforms, or did you not? Okay. E and t are similarly related because E is h bar omega, and just like x and k are Fourier transform pair of variables, and p is h bar k, so p and x can also be viewed in quantum as a Fourier transform related pair of variables. E is h bar omega, you may remember from the time dependence of the wave function. And omega and t are Fourier transform pair of variables, and since E is h bar omega, E and t are also a Fourier transform related pair of variables. And for similar logic that gives the uncertainty principle delta x delta p business, you get a delta E delta t type of relationship here, where the only way for a particle's energy to be perfectly well defined would be if its wave function's time dependence was e to the minus e t over h bar for all of time, present and future, back to t equals minus infinity and t equals plus infinity. There's no particle whose wave function has that time dependence forever because the wave function ends up changing. And so if it only has that time dependence for a finite amount of time, it actually doesn't have a perfectly well-defined energy. We don't have to go into any more detail than that, just kind of understand this idea that the finite lifetime of a particle means its energy isn't perfectly well defined, and delta E delta T is on the order of h bar, or in other words, the spread in the particle's energy, the uncertainty in the particle's energy, is on the order of h bar divided by the lifetime of the state in which the particle is with that energy. A detailed calculation shows that the, what's that? That's the,
Full width at half maximum.
yeah, full width at half maximum, or as we in the know say, the full width at half max. That the full width at half maximum, the full width half max is delta lambda sub 1/2, which means, that's another way to say full width half max here. That's the full width at half maximum, delta lambda at half the maximum width there basically, is equal to lambda squared over pi times c times 1 over delta t naught, where delta t naught is the average time required for the transition to occur. You can't say the time, because if you put a bunch of H atoms in n equals 2, let's say, they don't all decay down to the ground state at the same time. Because quantum, right, it's probabilistic. So you don't know how long any one of them is going to take to decay to the ground state. But there is a well-defined average. Delta T naught is the average time required for the transition to occur. And lambda is the nominal wavelength, the one that you would calculate, for example, for hydrogen using the simple Schrodinger equation or Bohr model. Lambda's the wavelength you get from the simple treatment, and this says, yeah, but even with no other factors, there's a spread in wavelengths that could actually be associated with that transition that could cause it or be emitted by it. And so let's give some numbers. For the H alpha line, now you're going to tell me what's H alpha, what are the principal quantum number values involved in H alpha? What transition is that for H alpha? So it's a Balmer series line, so therefore it starts or ends on n equals 2, and alpha will be the lowest energy one, and so that's the one that goes from 2 to what, or from what to 2? 3, yeah, so this is the 2 to 3 transition. N equals 2. 2 or from n equals 3, the Balmer alpha line, H alpha line. Lambda, the nominal wavelength, is 656.3 nanometers. I should have turned around and acted like you were supposed to know that. And then be like, oh my God, how do you not know this already? And then I'd be like, well, I know it because I'm looking at my notes, but shh, okay. Any sense of about how long it takes, if you put a hydrogen in n equals 2, about how long will it stay there before it drops to the ground state, for example? This is a typical time for atomic transitions like this. Turns out it's about 100 millionth of a second. About 1/100 millionth of a second is how long it'll take. So yeah, it kind of really wants to be down at the ground state. On the other hand, if you calculate in the Bohr model how many revolutions per second it's making, and you say, well, how many orbits does it make before it drops down? Because it's cheating, because it's not a Bohr model, it's not really revolving around it. But if my memory serves, I give that sometimes in Physics 280, it makes like 1 million orbits before it drops down, because it's orbiting a lot, It's like orbiting 1 million times in 100 millionth of a second. So in the Bohr model, that thing is whizzing, you may not realize that. That thing is whizzing, it makes like 10 to the 15th orbits per second or something like that. Anyway, that might be wrong, but anyway, it's on the order of 10 to the minus 8 seconds. So because the electron only spends about 10 to the minus 8 seconds in n equals 2, its energy isn't perfectly well defined as a result of that. And what we get from this is the natural width of the line, of the Balmer lines, is 2.4 times 10 to the minus 5 nanometers. 2.4 times 10 to the minus 5 nanometers. Does that impress you with how big it is or how small it is? I hope it impresses you with how small it is, because what did we say a typical equivalent width was for stellar spectral lines? Yeah, like 0.01 nanometers. That's tiny compared to 0.01 nanometers. So in other words, this must not be the major contribution in stars to the widths of the spectral lines. But it's still there, and as we'll see, it does play a role. It actually dominates the wings of the line. Conclusion, the natural width of visible spectral lines is generally quite small. It's not the major contribution overall to the line broadening. Okay, that fast clock is wrong. We still have another minute or two of precious education before the break, where I can give you, right, that's a detailed calculation. Let's do a quick and dirty estimate. Quick and dirty, okay? Quick and dirty estimate. A back of the envelope calculation. How can we come up with something that's close to being that formula, actually? Okay, so energy of a photon is, what do I put on top? The energy of a photon is what over the wavelength? HC, that's right. HC, as a matter of fact, yeah. The energy is HC over lambda. And of course, y'all know, not that I'm going to use it here, but you know that as soon as you see HC, why, you twitch as you think to yourself, why, that's EV nanometers. 1240 EV nanometers, right? Yep. HC, but here I'm just going to leave it as HC. Okay? So that means that we can relate delta E and delta lambda. Delta E should be equal to, thinking of this as taking a derivative, if you will, right? If I took dE lambda, what's dE lambda? If E is HC over lambda, what's dE lambda? Yeah, minus HC over lambda squared, right? Because lambda to the minus 1 differentiates to minus lambda to the minus 2. Okay, I don't want a minus sign here. So the absolute value of dE lambda, because I want delta E and delta lambda to just be positive spreads, essentially. But dE lambda would be then, as an absolute value, HC over lambda squared. So now, okay, but dE lambda, think of that as like being delta E over delta lambda. Change it like a spread in E over a spread in lambda. Another way to put it is, if I had some spread delta lambda, what would the spread delta E be? Well, you would get that from delta E is dE lambda delta lambda from, as an approximation, right? That's a general way to approximate a small change in a quantity. Delta E is approximately dE lambda times delta lambda. So let's apply that here. So then delta E should be HC over lambda squared delta lambda, based on that, right? Because that first piece is in absolute value, dE lambda. But we already said that delta E was H bar over delta T, roughly speaking. We're like, you know, this is like quick and dirty. So delta E is H bar over delta T. So H bar over delta T is HC over lambda squared delta lambda, or in other words, delta lambda is equal to lambda squared over Now, how did I get that? Let's see, where did I get that 2 from? Oh, yeah, no, I know what I was going to do, right, yeah. Yeah, HC, okay. But what's H bar equal to? So I'm going to add another line in here. H bar over delta T is, but what's H bar equal to? And I don't mean the number, I mean in terms of H, in terms of Planck's constant. Yeah, right, H bar is H over 2 pi. H over 2 pi, right? So this is H over 2 pi delta T is equal to HC over lambda squared delta lambda. Oh, now I can cancel the H's, right? Right? And so delta lambda is lambda squared over 2 pi c times 1 over delta t is what we get from this quick and dirty calculation. Oh, compared to the exact result, right? Awfully similar, isn't it? Other than the factor of 2 in the denominator, we got the same thing from quick and dirty.
Is it because that is the little bit at half max?
No, it's just because here we're just making, you know, rough approximations, and there it's doing fancy Fourier transform potato whatever stuff, you know. Yeah. Yes. It's always fun to do fancy Fourier transform potatoes. Yes. Okay, break time. Drive away. So one more thing to say about the natural broadening is that the profile associated with it, right, you can make a detailed plot of what it does to the shape of the spectral line, and we'll show something like that a bit later. It's also called the damping profile for a very interesting reason. Also called the damping profile because a damped harmonic oscillator with a charge attached to it would produce the same profile as an emission. A damped harmonic oscillator, oh, sorry, gotta spell it right. A damped harmonic oscillator with a charge attached would classically produce the same profile. So let's see. So y'all probably talked about damped harmonic motion in mechanics if you've taken it, right? So you have viscous damping, and so, right, if you have like versus time, right, the amplitude of the oscillations gets smaller and smaller and smaller. And so imagine that you had a spring with a charge attached to it, and there's damping, and you let that charge wiggle back and forth. Accelerated charges radiate. That's how you get classically electromagnetic radiation, is when charges accelerate, they radiate. And if you calculate what the plot of intensity versus wavelength would be for an electric charge that's undergoing damped harmonic motion, it's the damping profile. It's exactly the same thing, interesting, classically. And so that's why it's called this. In classical physics, to get radiation, you need accelerating charges. Charges just moving at a constant speed won't radiate. Charges that are just sitting there won't radiate. But if a charge is wiggling back and forth or otherwise accelerating, it gives off electromagnetic radiation. So if you had a charge on a spring undergoing damped harmonic oscillations, then it would produce an electromagnetic wave at any given point. It would look kind of like this. And if you find the Fourier transform of that, if you make a plot of intensity versus wavelength by Fourier transforming that, oh my gosh, it's the damping profile. In other words, the primary wavelength will correspond to how fast the thing is wiggling. It corresponds to the period of oscillation of it, turned into a wavelength from the speed of light. But there will be a spread because it's not a perfectly sinusoidal oscillation. A damped sinusoid is not a sinusoid. It's made up of an integral over sinusoids of different wavelengths. And so you'll get this narrow spread of wavelengths that are all contributing to it. Again, we don't have time to really go into this. I could literally spend the next 2 weeks deriving that in detail. Let's not. Okay, what questions do you have? All right. I mean, I'm tempted because I love Fourier transforms, but I think I should resist that temptation because this is not Fourier transform, math, or this turns out this is astrophysics. So, but I love Fourier transforms. If you've never watched the 3 blues, 1 brown videos about Fourier transforms and Fourier series, you are missing out. You should watch those magnificent works of art. Okay. Doppler broadening. 2, because it's effect number 2. Doppler broadening. So why would that be there? Let's talk qualitatively first. So, remember when I had like the hydrogen lamp out and you saw those lovely spectral lines when we looked through the diffraction grating? Even if the atoms were emitting one specific wavelength, we would still see a spread in wavelengths when we looked at that because that gas is hot. There's atoms moving every which way. If an atom is moving towards you, then that will cause a shift in the wavelength of the photon that it sends your way because it emits at the nominal wavelength in its rest frame. But if it's moving towards you and it spits a photon in your direction, what's that going to do to the wavelength of the photon? Moving towards, is that redshift or blue shift? Blue shift, so that'll shorten the wavelength, right? And if it's moving away from you, that'll lengthen the wavelength. If it's moving in an angle, it's only the component along the line of sight that matters. But the point is, you've got atoms that are moving in various directions at various speeds because they're freaking hot. And so that naturally produces a spread in Doppler shifts of the photons that they're sending your way, and that's Doppler broadening. You'll see a spread that will make the line broader than it would otherwise be because of this effect. And it works in absorption as well as emission because if the atoms are moving, then they will absorb the wavelength in their rest frame, that is the nominal wavelength, but in our frame, that's we'll see them absorb a different wavelength because they'll absorb a wavelength which they'll absorb a wavelength which looks a little bit different in our frame, but Doppler shifted by their motion is the nominal wavelength in their frame, as it were. And so this is why there's Doppler broadening. Doppler broadening due to the spread in Doppler shifts exhibited by absorbing and emitting absorbing or emitting. I'm saying absorbing because we're talking about stars, but if it's an interstellar nebula, then it's emission, if it's a glowing interstellar nebula. Due to the spread in Doppler shifts, exhibited by atoms I'll just say emitting or absorbing, because we could be talking about this for both emission lines and absorption lines. Emitting or absorbing photons Okay, I'm hoping this is turning into an intelligent sentence, because I don't want a hard time from Kathleen after I'm done writing it. Or absorbing photons, because they are moving. I'll just write it and see what happens. I'm in the middle here. Because they are moving at various speeds and angles to the line of sight. Angles to our line of sight. Okay, now let me read the whole thing and see what I've created. Does it make sense? Due to the spread in Doppler shifts exhibited by atoms emitting or absorbing photons because they are moving at various speeds and angles to our line of sight. Yeah, I think it basically makes sense. We'll go with that. You okay with it? Yeah, okay, all right. Okay, so first, the precise calculation based on the Maxwell-Boltzmann distribution, as in we'll give the result. We're not going to do the calculation because, it's tempting. It would be so fun, but we got other things to do. We got people to see. We got, all right, for a Maxwell-Boltzmann distribution. But then we can also do quick and dirty. For a Maxwell-Boltzmann distribution, right, that's the thermoequilibrium distribution of speeds in a gas. For a Maxwell-Boltzmann distribution of velocities, the detailed calculation says the full width at half max, the delta lambda sub 1/2, is 2 times lambda over c, where lambda is again the nominal wavelength you would get from the Schrodinger equation, finding the difference in the energies, blibbity blobbity blue. 2 lambda over c times the square root of 2 kt times the natural logarithm of 2 divided by the mass of the atom. Divided by the mass of the atoms that are responsible for the spectral line. But never let it be said that if we had a chance to get our hands quick and dirty involved in this, that we failed to take it. Quick and dirty. Anybody want to blow my mind by reminding me from the Maxwell-Boltzmann distribution what the square root of 2 kt over m is?
Most probable velocity.
Yes! It is VMP, the most probable speed, yes. VMP, the most probable speed, or even physicists will say velocity, right? Most probable speed. I mean, we make so much like, song and dance to freshmen. It's like, now there's a difference between speed and velocity. Velocity is a vector, and speed is the magnitude. It doesn't have direction. And then we're like, and the escape velocity is, right, stop it. We're not hypocrites. Most probable speed, but you hear people say most probable velocity. Most probable speed. That's the most probable speed from the Maxwell-Boltzmann distribution. And so the Doppler shift formula is delta lambda over lambda is equal to the radial velocity over the speed of light. Have you seen that before? So change in wavelength over wavelength is the radial velocity, the line of sight velocity, divided by the speed of light. That's the non-relativistic approximation. Yes?
Is that ln of 2 in the numerator?
It is. It's the natural logarithm of 2. Yes. Yep. You knew that, right, Kathleen?
It took me a little bit.
It took you a little. Yeah, it took you a little. Yeah.
It's written really nicely.
Yes.
Yeah, it's
Just
just,
seeing it written.
right, yeah, okay, very good, yes. All right. So I'll point out, here's the Doppler shift formula, just in case you need a reminder. Right? Only the radial velocity, the line of sight velocity matters. So delta lambda over lambda is v radial over speed, c. Well, delta lambda over lambda is approximately 2v most probable over c, would be a rough estimate for the Doppler broadening. Would be a rough estimate for the Doppler broadening line width, and I'm going to ask you why that is in a minute, so be thinking about it. It's a lot of pressure here. Right, so in other words, this would be saying, if I did this, this would be saying, oh, we think that delta lambda should be approximately equal to 2 times the 2 over c times the square root of 2kt over m. Oh my gosh. Delta lambda over lambda, so 2 lambda over c times root 2 kt over m. All we're missing is the natural log of 2 from the more detailed treatment. So again, quick and dirty got us most of the way there. So why would 2v most probable over c be a good estimate of the Doppler broadening? Where's the 2 coming from? Yes?
From the fact that it could go in either.
Yeah, right. In other words, think of like v most probable as kind of a typical speed, if you will, and you could get a blue shift if it's headed towards you, or a red shift if it's headed away from you, and those will have equal and opposite delta lambdas in those two cases, so the total spread should be about twice that. Right? Some blue shift, some red shift, so the total spread will be what you get from including both blue shift and red shift, and so that's why you got to have a factor of 2 here. And it's also there because it makes it come closer to the right result, but that's, you know, that's the idea. And again, detailed treatment is going to account for the fact that, well, yeah, they're not all moving at v most probable. There's the whole Maxwell-Boltzmann distribution of speeds, and they could be moving at any random angle to the line of sight, and so you got to do some fancy integral, la 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 la, and the result is blah, blah, and then we do our simple, quick and dirty calculation, and the result is blue, blue, and all we're missing is log 2. And so, cool, we came that close with just quick and dirty, right? Lovely. All right, what questions do you have? Of course, now we want to throw in some estimates here. You look like you're pondering a question. Are you pondering a question? Or are you just...
Sure, I'm just walking myself through it.
Okay, okay. Okay, all right. Keep on walking later if you want, and, you know, talk to your... It's a very low bar here because there's not a lot of competition. Come see your favorite astrophysics professor this whole semester and talk about it some more. Yeah, I like things like that, right, where I can confidently state, right, you know, like my wife, I am her favorite husband, you know, for example. Anyway, for the H alpha line, at the solar photospheric temperature of 5,770 Kelvin, at the solar photospheric temperature of 5,770 Kelvin, solar photosphere temperature T equals 5770 Kelvin. Okay, it's really tough, shut up. 5770 Kelvin. Good enough. Turns out that the Doppler broadening width is 0.0355 nanometers for the H alpha line, which, while not huge, is about 1,500 times broader than the natural width. So in other words, Doppler broadening is a lot more important than natural broadening in terms of the overall width of the spectral line, of visible spectral lines. And you might say, oh, well, that's more than 0.01 nanometers. Hey, I said it's on the order of 0.01 nanometers. That's still on the order of 0.01 nanometers. So give me a break, it's fine. Okay, questions, comments, observations? I'm waiting because I want people to write down things, yes? I'm patient. I do need my button that I can push that starts playing a little music in intervals like this. Maybe you'd be like, dum, 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 dum. Yeah, except, so I decided to do my noon workout instead of going to the Jeopardy, the Wins Jeopardy. I asked Dr. Trees how it went. He told me I made the right choice. Did any of you go to the Wins Jeopardy? Okay. The Wins Jeopardy where they, you know, have Jeopardy and departments compete with one another.
I went to that one time, yeah.
What's that?
I think I went to that one time.
Yeah, it was in the noon hour today. Yeah. So back in the day, we had the winning streak. We used to win all the time, and it was partly because I tended to know the answers to the questions. And so my colleagues would beg me to come to Jeopardy so that we could win. Yeah. So I don't know the answers anymore. They used to ask different kinds of questions somehow, so I don't tend to know them anymore. But so it's not as interesting to me anymore. It's not glorious enough anymore. Okay, have I blabbled enough that we can continue here? Okay, so new concept. So do you all know what turbulence is? So if you have a fluid, right, you can have like parcels going every which way. It can be all very complicated. Later on, we'll talk about convection, which can be turbulent and so forth in stars and in everywhere. So in a stellar atmosphere, you can certainly have turbulence. Like the sun, the photosphere, it's convective. There's rising and falling parcels of gas and so forth. And the idea here then is to think, okay, well, not only can you have a Doppler broadening due to individual atoms moving every which way to the line of sight, you can also have a form of Doppler broadening due to blobs of gas moving every which way to the line of sight. And if you have blobs of gas moving every which way, they all have their own Doppler shifts. And so it's like a macroscopic version. And we need to include that in the Doppler broadening. So if the gas is turbulent, oh, stop squeaking. If the gas is turbulent, this also broadens the lines. And this is a big if the turbulent, I guess it's my fault again, I don't know. Wow, okay. That's very dignified. If the blobs have a Maxwell-Boltzmann distribution, shady, but you know, whatever. If the blobs, if the turbulent gas blobs have a Maxwell-Boltzmann distribution. It's too much work to write Maxwell-Boltzmann again, so I just said M-B distribution. Then they add in quadrature. In other words, we get delta lambda sub 1/2, the 4th half max, it's 2 lambda over c again, square root of 2kt over m, which is VMP squared, right? That's VMP squared. That's VMP squared. Plus V turb squared, natural log of 2. In other words, you just get another term that corresponds to the most probable speed of the turbulent blobs. That's what V turb is. So I'll write that over here in some random place, and you can write it in your notes in a not random place. Most probable speed of the blobs. Sounds like a science fiction thing, right? The blob or something like that. Which turns out has been my nickname at various times. In fact, my siblings, yeah, because I'm Bob. So of course you have to, you know, of course you have to find ways to tease people. And so sometimes my siblings call me Blob. Now, I was the oldest, and it was my job, therefore, as the oldest, to torture them when they were kids. But at the same time, I gave them horsey rides and stuff like that, you know, so there is a balance to all of this. All right. Okay. Gotta add something here. The line depth in the wings, right, the further away from the center parts, the line depth in the wings falls off exponentially. And that's because the Maxwell-Boltzmann distribution falls off exponentially. Falls off exponentially much faster than for natural broadening. Much faster than for natural broadening. And later we're going to make a statement based on this, that spectral lines have Doppler cores and damping wings. In other words, the spread in the core is mostly due to Doppler shifting, but while the damping produces overall a very narrow equivalent width or full width half max to the spectral line, it falls off slower as you move away from the center. So far from the center of the line, most of the absorption is due to the damping profile. And so we say spectral lines have Doppler cores and damping wings, so to speak, which is vaguely poetic, right? Spectral lines have Doppler cores and damping wings. Anyway, okay, questions? And I'll just throw in here, I said it, but this is due to the exponential tail of the Maxwell-Boltzmann distribution. Right, because it's at e to the minus mv squared over 2kt, so it falls off exponentially. Due to the exponential tail of the distribution. Maxwell-Boltzmann distribution. Three. We've mentioned this before, we'll do it again. Pressure and collisional broadening. They're related to one another, and they have very similar effects. And this we met before, and we'll say some more about it now, when we talked about why are the spectral lines of giants narrower than the spectral lines of main sequence stars. It's because of this phenomenon. So, we will see if you respond to this in the way that tells me, well, I don't know what it'll tell me. So I'm going to say close encounters with other atoms and ions. And as soon as I write that part, I'm going to reread it again. And this is not going to work well because my voice doesn't always work well, but close encounters. That's a totally, God. I should have had a like a, I just won't even try to. Do. Does that mean anything to you? Close encounters. Do. Yeah?
I've seen it, yeah.
You've seen it, yeah. You've seen it, yeah. You're looking at me like I've got two heads. It's a movie, yeah. Close Encounters of the Third Kind. Right. 1977, same year as Star Wars. Steven Spielberg, where humans are visited by aliens. A Close Encounter of the Third Kind is where you actually see the aliens. And so the movie is where humanity first encounters aliens in person, so to speak, or in whatever their species is. And the aliens and the humans communicate with tones, basically. And so it goes do. There's a famous scene in the movie where they're playing that back and forth to themselves, to one another, and then it starts going do. So anyway, close encounters do at a higher pitch than that with other atoms and ions. That was a very long-winded way to justify, because there are things I just can't help, right? Every time I say this, I hear do in my head, so I thought I would share. Just like, and we'll see this later, why when helium burning begins in the degenerate core of a low-mass star, it does so explosively in the helium flash. Thank you, yes, thank you. Because of Queen's Flash Gordon theme music from 1980, terrible movie, much better song. And so literally when I say helium flash, goes off in my head. And so therefore, my students need to say You're all going to be saying when we talk about the helium flash in the core, helium shell flashes. Every time I say it, you're going to say even if I don't tell you to. Close encounters. Thank you. With other atoms and ions. Subject an atom to rapidly varying electric fields. You all have heard of like van der Waals forces, where there's residual electric fields that atoms and molecules exert on one another when they're nearby. Subject an atom to rapidly varying electric fields, because, here's another atom or an ion or whatever. Well, when it's closer, that electric field is stronger, and when it's weaker, it's further away. So you can think of the atoms are in these rapidly time-varying electric fields, and if you stick an atom into an electric field, you've added a term to the Hamiltonian, which will shift the energies. So in other words, when we calculate the energies of, say, the hydrogen atom, we're treating it as it's isolated, it's the only thing in the universe. If you put it in an electric field, that shifts all the energies. You've got all these close encounters that keep distorting the orbitals and shifting their energies. And so if you got a whole gas of this happening, you've got a spread in the energies of the atoms that are emitting and absorbing photons. You have pressure broadening. And it's called pressure broadening because the higher the pressure, the more encounters there are, right? So it's correlated with the pressure. It's not really caused by the pressure per se, but higher pressure means more of these encounters, so it's correlated with it. And since it gets called pressure broadening, and astronomers will call it that because it shows up as, well, the lower pressure in giant atmospheres is associated with narrow spectral lines because there are fewer close encounters, and so this is a smaller effect when the atoms and ions are further apart from one another, and that'll happen when the pressure's lower. So, close encounters, wow, I really can't do the high-pitched thing there. Close encounters, okay, not bad, thank you, with other atoms and ions, subjects an atom to rapidly varying electric fields which perturb the energy levels. So this is another quantum effect in the end. If you have a static electric field, this comes under what's called the linear Stark effect. But here they're rapidly varying, so it's almost like, well, do the Stark effect for lots and lots of values of the electric field. If we have an ensemble, you know, it just has to be true. Somebody who speaks French is going to confirm this. That has to be a word we got from French. It just has to be. Yeah. Ensemble of absorbing or emitting atoms I mean, English is a Germanic language, but we've got more Romance language words in our vocabulary than we do German words in the end. Absorbing or emitting atoms. This effectively spreads out the energy levels, thereby broadening the spectral line. Spectral lines. Every atom's got a slightly different energy when it's emitting a photon because its environment of nearby electric fields from other atoms is a bit different from other atoms. This spreads out the energy levels and broadens, thereby broadening the spectral lines. So note that, you know, this goes both back and forth. In other words, if you know the conditions of the gas, you can predict what it's going to do to the spectral lines. Conversely, if you study the spectral lines in detail, you can deduce things about the conditions of the gas in which they're formed. Hence this idea that spectral lines are an important diagnostic. They're a very powerful tool in the right hands. Mine aren't the right hands, I'm not an expert on this, but in the right hands, they can be a very powerful tool. This is called pressure broadening. That's the pressure broadening part of things. But there's a related effect, and that is, he said, waiting for people to catch up. So remember our, are you still writing? I'm not actually. You're good? You sure? I spoke too soon, maybe. I don't want to interrupt. Okay. So remember we talked about that hypothetical hydrogen atom sitting at n equals 2, and how long would it be on average before it drops down to n equals 1, roughly speaking? What did we say that was about? Like 100 millionth of a second, right? here's something that can make it happen quicker. Hi, I'm a hydrogen atom. My electron's in n equals 2. Oh, I just hit another hydrogen atom or something else, and the electron changed its energies as a result of that. So you can get the electrons to prematurely change energies because of collisions, shortening the lifetimes of the states, broadening their energies because of the delta E, delta T is roughly h bar. If you shorten the lifetimes because collisions are making electrons transition too soon, quote unquote, you've increased the uncertainty in the energies of the levels by that delta E, delta T is approximately h bar business. So that's what this is about. So new line here, collisions between atoms, or between atoms and electrons, but I'll just leave it. Collisions between atoms or other particles can cause an atom to de-excite sooner than it otherwise would. Just occurred to me that, like on the video, that's going to just be off stage, so to speak, right? There's all of a sudden crash, you know? Yeah. Otherwise, would. I almost wrote W-O-O-D. Otherwise would. Yeah, I could have gotten you all in on this, right? It'd be like, you know, I do that, and you're like, oh my God, are you okay, Dr. Harvard? Yeah, I'm fine, just punking y'all, right, or something like that. Yeah. Then it otherwise would, effectively reducing the lifetime of the state, and thus increasing delta E, and broadening the line. Let's see. Effectively reducing the lifetime of the state. Yeah, one year in 110, or no, it was 111, I think. You can never distract me. So I'm giving back the exams, and I like to just like run around handing people their exams in the room. I like to deliver them personally. And I come over here, and it's like my right leg crosses my left leg, and I went bam, very hard against the wall, and fell down, and there was a visible like, you know, in the room or whatever. And it turns out I did get a little bit of a bump, but so I'm down there, I'm down on the ground for a minute, everybody's like, oh my God. But I was fine, I felt, so I got up, you know, no, I'm fine, I don't think I've got any Dane bramage, you know, and stuff like that. And the nice thing is, I didn't even see this happen, afterwards, there was a little piece of candy on the table, and somebody had said, sorry to hit your head, hope this makes you feel better, or something like that. I'm like, oh, you know. So anyway, what's that?
Happened this semester?
No, it was a couple of semesters, yeah.
I was there, I saw you.
You were, did you see that? Or?
Yeah,
oh.
It was this,
oh, that was when you were, oh, okay, yeah. Was it might have been the next class where the thing came up.
You've been in class that I was in too, so maybe
yeah, here, we might as well just make this, okay, yeah. Yeah, that's right, third time's the charm, right? It's for some reason, and my wife's always afraid my antics are gonna cause some big problem someday. But anyway, she hates the fact that I stand on a ladder and throw things at people. Reducing the lifetime of the state. As far as I know, she hasn't taken out any insurance policies, but the lifetime of the state. Where were we? Thus increasing delta E and broadening the line. And so this is collisional broadening, obviously. In both cases, the degree of broadening is determined by the mean time between close encounters or collisions. That's like related to the mean free path, right? Yeah. Oh, sorry. No, please, yes. Right. In both, well, here it comes. We had an opportunity. In both cases, right, pressure and collisional, in both cases, the degree of broadening is determined by, that's going to get especially illegible if I keep trying to write down there. Is determined by, is determined by the mean time between close encounters. Okay.
They don't know it, they've seen the movie.
It's true.
Yeah, okay.
Watch the clip.
Yeah, I probably should. Yeah, well, next time maybe we'll watch the clip, right? Between close encounters and collisions. Where am I? Let's see. Which for collisions is of order because for close encounters, well, how close is close? It's a little bit sloppier. Which for collisions is of order, we'll call it delta T naught, should be, oh, that'd be like L over V. What should L be there? Colgate toothpaste with maximum fluoride protection, MFP, which stands for mean free path. This should be the mean free path, right? Mean free path over how fast they're going, right? That'll be a time scale. You did that in one of the homework problems. Equals, well, we already saw before, that's 1 over n sigma was the mean free path, right? And then for V, we could use, again, root 2 kt over m. And is the number density. And sigma is the collision cross-section. So this time we'll just do quick and dirty. And now I've got, who does that? Like Riding Dirty, you know that song? It's like, yeah, right. Yeah, like I'm going to roll with or something like that. Now I can't think of the words, but right. We're going to do it quick and dirty. Going to do it quick and dirty or something like that. Anyway, so quick and dirty here. Would say delta lambda 1/2 is lambda squared over pi c times 1 over delta t naught. Oh, I forgot to say something. Quick and dirty, I forgot to say, somewhere I have to say this. Okay, I'm saying it random. This is supposed to be higher up. turns out both collisional and pressure broadening have a damping profile. And so we can use the formula for the damping profile, which was the first one we did, natural broadening. Both collision and, oh, stop it. Both collision and pressure broadening have a damping profile. There's the waving chicken feet, so I just take my word on that. So we can use the damping profile, lambda squared over pi c times 1 over delta T naught, but if for 1 over delta T naught we use the reciprocal of this, then we get that it should be on the order of lambda squared over pi c times, and stop it. Okay, I'll tell you where my serial number and where, anyway, times KT over M. It's like the whole, claw, metal claw, and why does that bother people so much? I don't know why that is. There must be like some evolutionary, reason for that. Maybe it sounds like the screech of a bird of prey that's about to carry you off to its nest or something like that. So I might have seen that once as a speculation. Anyway, blah, blah, blah. So the line width depends on the number density. And it's time to go. Next time we'll finish up this thought by saying, back to, well, the number density is lower in giant stars because their atmospheres are more spread out, and so they have less pressure broadening, accounting for their narrower spectral lines compared to main sequence stars, blah, blah, blah. This is a more precise way to say what we were saying earlier. Yeah, and then it'll be glorious. We'll move into chapter 10, where we'll study stellar structure, the equations of stellar structure. It's going to be glorious. I'm excited. I'm very excited for it. Yes. And it's the same kind of stuff that you need to study Earth's atmosphere. I'm just saying,
Traumatized from my Ireland class.
You're still traumatized, huh? Really? I'm trying to untraumatize you here.
Well, yeah.
Okay, all right. I probably shouldn't be having this on the, yeah. Yeah, but no.
Equations, you know how to derive that.
Oh, yeah. Okay. Well, different